Hello and welcome to this design practice 2 module 20. So we were talking in the last lecture about the numeric valve design shown and represented in this diagram right here. Some of the parameters that are there are this that the microvalve has a circular silicon membrane and which acts as a valve seat. The membrane is about 20 microns thick, which is given right here, and has a diameter of about 4 mm, 400 microns, and the valve is normally open with a gap of 20 microns. So this distance right here is 20 microns when it is normally open between the membrane and the valve inlet. This is the inlet. So I will just write the inlet channel here. This is the inlet. The idea is that this membrane will bend down, as you are seeing in the dotted region here, and it will close the inlet so that the valve can come to the closure position. And you have to determine the pressure required for closing the valve at an inlet pressure of 1 bar. So you are wanting to determine what is the pressure requirement on the other side of this membrane, so that you know a total pressure of 1 bar in inflow could be controlled, could be blocked. Given that the opening diameter is about 200 microns, where this whole pressure is being exerted, and we have to assume a distributed load on the valve membrane. So we can't assume a point load here. It is as if a cylinder is giving air pressure, okay, something like that, and so it is well distributed load on the whole membrane, the blocking membrane, or what you call the valve seat. And you have a Poisson's ratio of about 0.25 and a bulk modulus of 170 GPa for silicon material through which this valve has been constructed. So let us do some preliminary calculations. So for a small deflection, the spring constant of the uniformly loaded valve membrane is estimated as K equals to 16 pi E cube of T divided by 3 R square 1 minus nu square. I am just going to refer the various terms here. E is the bulk modulus, T is the membrane thickness, and this is from standard strength of material knowledge that the computation for K or the solution for K is being borrowed. R is the total radius of the membrane. So I call this membrane radius, and nu is the Poisson's ratio of the material. In this case it is silicon. So the Poisson's ratio has been given out to be about 0.25 in this particular case, and we want to calculate what is the value of K for this particular problem. So therefore K comes out to be equal to 16 times 3.14 value of pi times of the total bulk modulus, which is about 170 gigapascals. So I write it 170 10 to the power of 9 pascals times of cube of T. You know the thickness T is given out to be 20 microns. So we have 20 into 10 to the power of minus 6 meters, and cube of T divided by 3 R square. R in this particular case is about 2 millimeters. If you remember, the total diameter here is about 4 millimeters, as can be seen in this of the whole valve membrane, and so we are going to go halfway when it is radius 2000 microns or 2 millimeters. So we have square of R, which is 2 into 10 to the power of minus 3 square times of 1 minus 0.25 square as the Poisson's ratio, and this is found as 6.08 10 to the power of 3 Newton per meter. So that is the equivalent spring constant that is found in this particular case for the silicon membrane, which is going to be acting as a valve seat. So, let us assume that the microvalve is closed at an actuation pressure P act, and this pressure per se falls on the top of this membrane. So, you know that the closure can only happen if there is some kind of a uniform loading and in terms of force per unit area or pressure on the free end of the membrane, the microvalve membrane. So, if you assume this area of the interface to be AM, let us say the area of the membrane. So, we have P actuation on one side and on another side the inlet pressure. So, if we further assume the area of this opening right here to be A open, okay, we can have a force diagram of this particular system. So, the force balance on the membrane is P actuation times of area of membrane AM equals the inlet pressure times of area of the open channel A open plus the spring force that the membrane has to exert, which is towards the opening side, because obviously you are bend holding the pressure inside this particular pipe, you know, or in this particular inlet wing, and for that whatever force is needed to bend the spring is going to give a reverse force as if the spring were open and it would try to close. So, it will give exactly kx force where k being the spring constant. So, k has already been calculated in this particular case. So, let us calculate this force balance equation for two different conditions. One, when the valve is in an equilibrium state, and let us say we are talking about the equilibrium at valve closure, and we can also find out the total amount of, you know, how this equation behaves at valve opening, okay, as the actuation begins. What is interesting in this case would be that both these values are quite dissimilar, and one has to design for all this when you are talking about such a actuator design, okay, which is going to do valving, okay, at this particular scale. So, case 1 is corresponding to when the actuation begins, and case 2 is corresponding to when it is an equilibrium. So, let us understand properly what happens to case 1, that is when actuation has begun to happen, actuation begins. So, you have a case where you have the P act on one side with the membrane radius and the area therein, the area AM in this particular case, as you may recall, is given by pi rm square, where rm is the 2 millimeters radius of the circular valve orientation which has been defined earlier. So, this becomes equal to that on the inlet side, again pi rm square. Please understand, when we are talking about beginning of actuation, the whole inlet pressure is available on the lower side of the membrane, because the membrane has not deflected or moved, and so the membrane is being upheld by the inlet pressure, which gets into this particular channel and before moving out would create through the Pascal's law an equal pressure in all directions. So, here the Pi or P in times of pi rm square plus the spring force is what makes up the force balance equation. We can divide by pi rm square. So, we have P inlet plus the total spring force kx in this particular case divided by pi rm square, inlet pressure being equal to 1 bar the spring force being equal to the K value times the total amount of deflection that it has to withstand, which is 20 microns. For opening to closing, you have to cover this particular distance of 20 microns, okay, divided by 3.14 times 2 10 to the power of minus 3 square. So, that comes out to be equal to about 109,677 pascals. So, this is how the beginning pressure is when the valve actuation has started. However, in this particular case you may observe that when the valve actually closes, so much of pressure may not be really needed, okay. It is going to change when it is at equilibrium. So, the actuation force or the actuation pressure is going to be the highest pressure in this particular case. So, this gives you an idea of how you are designing a valve actuator, okay. In the same manner, I am going to do a few things, in the next few minutes with you, which talks about such actuation principles and designs. So, here in this case, in case 2, let us say when at equilibrium, when the valve is in closed position at equilibrium, the P actuation needed would be much lesser. Obviously, the fundamental that is kept intact here is that the spring force of course is K into 20 minus 6, and the actuation force times of the total membrane area becomes equal to the total amount of inlet pressure times the inlet area, which is only 0.1 in this particular case, okay. You know that the opening dia here has been given to be about 200 microns. So, that is about 1.1 millimeters radius. So, let us put this value back here. So, we have 0.1 times of 10 to the power of minus 3 square as the force on the inlet side. You have to consider the valve in closed position, where the only exposed part of the valve lower membrane, okay, is 0.1 millimeter radius circle, okay, valve inlet force. So, this plus the spring force, which is in this case 6.08 10 to the power of 3 times of the total movement that has happened, which is 20 microns. And in this case, if I calculated what is the actuation pressure, it comes out to be equal to 9.85 10 to the power of 3, that is about 9850 pascals. So, it is very clear that actuation demands a lot more energy in this particular case than equilibrium and closure. Demands a lot more energy. In this case, energy is of course given externally by a mechanism which would exert pressure on the membrane, which will close the flow. So, it demands a lot more energy than maintaining the closed state. Here the total amount of pressure needed is about close to 109,677 pascals, whereas in the closed state you only need about 9850 pascals. This is true for all actuator systems, that when we are talking about start of actuation which leads to a certain end effect, it is almost always that more energy has to be pumped in the system than the end of the actuation. So, we will design the corresponding thermopneumatic version in this particular case. I am going to twist the problem a little bit, and here what we simply say is that the valve described in the earlier example is designed with a actuator which is of thermopneumatic type on the top of the membrane, thereby meaning that there is a cylinder on the top which has a fixed volume containment or a confinement and heaters which would heat the gas, and so the gas inside the confinement would actually follow the Charles' law of pressure being proportional to the temperature. So, with the temperature rise obviously is going to give more and more pressure onto the membrane, thus deflecting the membrane and blocking the valve. So, in that event what is going to be the temperature required for closing the valve? Okay. We will assume the same inlet pressure of 1 bar as earlier, and we can assume the initial pressure and temperature of the chamber to be 1 bar and 27 degrees Celsius respectively. Obviously, we assume that the chamber is filled with air and hermetically sealed, so that there are no heat outlets, heat outlets from the system. So, assuming that in this particular case the chamber is constant, the relation between temperature and pressure, if it is hermetically sealed and if there is no heat inlet outlet to the chamber except the heater which delivers the heat inside the chamber itself. So, you have T1 by T2, that is the temperature ratio between the initial temperature T1 and the final temperature T2 being proportional to the pressure ratio, that is P1 by P2. And so, therefore, the temperature that is needed for a pressure rise, which is equal to the force needed for actuation. In this case, you already found out the total amount of pressure that is needed for actuating or start of actuation of the valve is 109,677. This comes out to be equal to the pressure ratio between the actuation pressure and what it was earlier at. The pressure was earlier at 100,000, 1 bar inside the cylinder, okay, and the earlier temperature was 300 degrees. It has been mentioned here 27 degree or 300 degree Kelvin, okay. So, a total amount of temperature that is needed for this process to execute the valve closure and then becomes about 56 degrees Celsius or 329 Kelvin. So, that is how you design a thermopneumatic system. So, there can be many such forms of systems which are used by various different valves. They particularly can operate on a lot of conditions. For example, there can be as I told you, thermomechanical valves, there can be piezoelectric valves, there can be electrostatic valves, there can be electromagnetic valves, so on and so forth. So, we would now like to design another set of actuator, that is an electrochemical actuator, which would be playing the role of an electrochemical microvalve. Of particular importance here for me to tell you is that such valves are very commonly available within microflows and microfluidic systems, because they are typically electrically driven, and it is always better from an integration possibility into a chip scale. So, microchip scale. So, this is what we want to do here. We have case 1, a certain layout of the electrochemical valve where there is an inlet of a flow coming from one end and an outlet going to this end, and there is a possibility of these electrochemical bubbles which are being formulated by hydrolysis of water, and there is a reaction element which is there where H2O is converted into hydrogen and oxygen gas, and obviously because there is a certain dissolution rate within the medium which may be quite different than the formation rate, and formation rate may be much ahead of the dissolution rate. So, whatever is not dissolved is stored inside the water as a pocket, so it becomes a bubble, okay. So, it is a two phase bubble where there is a gas phase which is being surrounded by the liquid water, part of which has been hydrolyzed into the gas, and so such bubbles and the way that it grows or the rate at which they grow can be customized in a manner which would lead to eventually the movement of this gate. So, for example, if these two bubbles right here are smaller or their growth rate is smaller in comparison to the bubbles which are at the back end here, then obviously the gate will move forward. And supposing is the other way around, that the two bubbles at the so in the closed position of the valve, the two bubbles at the front end are being created at a much higher rate in comparison to the bubbles at the back. So, it may lead to a reverse possibility, that is the gate going back and allowing the flow to happen. So, this is one version. The other version could be in terms of a bubble which you are formulating in a channel. This bubble right here generated somewhere inside this microchannel may become so big that it starts blocking all the inlet from going through the small constriction which is there. So, obviously, the total amount of bubble pressure which has to be there should be enabled to take the inlet pressure and still retain its property of being a bubble. So, one of the advantages that microscale flows have is a lot of difference in the physics. It is more surface based physics, where effects like surface tension etc. has a predominance over the volume effects like density, pressure etc. So, electrochemical valves in that range work very well. And so, the whole idea is to design again an actuator or a valve which is based on electrochemistry, as I showed you just above here in the two cases. Some of the parameters have been given. So, we would like to determine the energy required for generating an electrolysis driven spherical bubble with an approximate diameter of 28 microns, and we would like to generate this bubble electrochemically and compare it to the amount of thermal bubble effort. So, if supposing there is an equivalent bubble created by just heating and vaporizing, so what is going to be the difference in terms of energy in both the cases, in the electrochemical as well as the thermal cases, particularly if the bubble were of the same size. Okay. Some parameters have been given here. For example, specific density of hydrogen and oxygen have been given at 1 bar pressure and 25 degrees Celsius. This is the standard temperature conditions, standard temperature and pressure conditions, STP conditions, and they are 0.08988 kg per meter cube and 1.429 kg per meter cube respectively. Similarly, component related to surface tension of the water has been given. So, it is very important to see what are the pressure differences which would be sustained by the bubble. Okay, pressure differences between inside the bubble and outside the bubble. So, we will try to design it on that basis. Surface tension of water is given at 0.072 Newton per meter, and then we have some other parameters including enthalpy of formation of water, which is actually related to the way that this electrochemical reaction happens. This is the enthalpy for this particular reaction, and some thermodynamic properties of liquid water, particularly at the same pressure level, at same temperature level, that is the total amount of specific volume or the internal energy that the bubble will have if formulated thermally. And further, these parameters, that is specific volume as well as the internal energy, are given at the boiling point as well as the room temperature point. So, there is obviously going to be a change in these properties as the temperature goes up. So, given all these parameters, let us have a discussion probably in the next module as to how do we compare these two processes in terms of the energy requirement, so that the actuation can happen electrochemically, and we would get an understanding, a fair understanding of the very fact that in electrochemical actuation techniques, the demand for energy may be much more in comparison to the thermal technique. So, we will round off this module here, but in the next module we will try to do design of this particular valve. As of now, thank you very much and see you in the next module. Bye.